this computer. Okay, got it. All right, now you're all set. All right, everybody knows Landon, so I will not spend too much time on introduction. Landon's been here 5 years. Before that, he was at Miami, got his PhD from Oklahoma State. Works in a variety of areas, including ophthalmology, all the way to composites, and looking at materials aspects and strengths and things like that. And also, he was very instrumental in leading our PPE effort last year and supplying over 15,000 face masks to hospitals.
150,000.
Sorry, I made the mistake. Order of magnitude wrong. Just an order of magnitude wrong. But 150,000. I knew it was on 15 somewhere. Sorry. And quite a few hospitals sent back thanks to us for the department. Of course, it was all Landon and his team of graduate students that worked on this. So given all that, Landon is up for promotion and tenure this year, and this is a seminar. We are recording it, so for faculty, many faculty who cannot be here can watch it later. So Landon can explain about his research in his own words. So Landon, take it away.
All right, thank you for that introduction, and especially about the PPE stuff. I'll actually, if I have time, I'll talk for 5 minutes about that kind of at the end. But first of all, I wanted to say thanks to everyone for letting me reschedule this, and hopefully most of you can watch the recording here. But as we were talking about before we hit the recording, most of you may know, but what happened was I had a cut on my finger and cleaned out my daughter's fish tank, and apparently there's some nasty bacteria in it, and before I knew it, I had black streaks on my arm and fever and the whole 9 yards. But because of good antibiotics, I am now recovered. So in the future, I'll be wearing gloves when I clean out fish tanks or getting rid of her fish tank altogether. Anyway, like most people, I felt pretty isolated from the department over the last 2 years. So I'm looking forward to bringing everybody kind of up to speed on what I've been working on. I've been pretty busy, to say the least. Have enough funded research going on. Fortunately, I was able to buy out my class this semester, which is the first time in 9 years, 18 consecutive semesters that I haven't taught a large class, which has been strange, but also really great as well. So the main topic I want to focus on is actually the subject of my career award, or a portion of the career award, which is using molecular water as an imaging agent for the detection of damage in polymer composites. About halfway through the project at this point, a little behind in terms of spending, so maybe not quite halfway in terms of spending just due to COVID. All right, so I'm going to spend some time on the background and motivation for the work, including the path that led me to it. Then I'll speak about some of the fundamentals that enable the work and the methodology that we use, followed by some of the results, and specifically some of the challenges we faced and limitations associated with the method, and things we're exploring to overcome some of those challenges. And toward the end of the seminar, I want to spend just a little bit of time talking about my work with the NIH. Srinath alluded to my work in ophthalmology, so I'll talk about that a little bit. Also want to talk about these particular funding mechanisms that I think are underutilized and that I've had good success with. And I want to talk about one project where we're leveraging pressure sensing composites and some machine learning to do some exciting things in the medical device field. And lastly, I haven't seen most people since the pandemic started, so I wanted to bring you up to speed on what I was up to during those early days of the pandemic, which seemed like a decade ago, but was just last year. So going all the way back for a second to 2007. So I was accepted into the Palace Acquire program and went to work for the Air Force. And I developed an interest in a pretty specific area of mechanics and materials. At that time, I was doing a lot of work on older airframes. So the B-52, the B-1, the B-2, the KC-135, E-3, things that were designed, 40s, 50s, 60s, 70s, and had been operational for decades. And one of the things I realized very quickly was that, material properties aren't static, right? They're not set. As engineers, we make that assumption pretty regularly that these are the material properties, we use these for design, but in reality, the relationship between a material and its environment is pretty dynamic. So materials respond to their environment for the most part in negative ways. And this is particularly true for polymers and their composites. But over those 5 years I spent with the Air Force, understanding how materials evolve in various ways, to various environments, and what that means for us as engineers was an interest that really took hold. So my dissertation, which I started shortly after that, focused on one aspect of that environmental response, which was moisture diffusion and the associated degradation in material properties from that. So almost everybody knows probably, we've been using Fickian diffusion and Fick's laws for decades to describe moisture absorption in polymers. So simple, concentration gradient driven diffusion, Brownian motion, but in reality, the process is far more complex than that. And at longer time scales, similar to what we see on composite structures that have been around for decades, the difference between Fickian diffusion and reality becomes pretty important. So there's a number of different mechanisms that are happening alongside Fickian diffusion in response to the presence of water. Relaxation is the big one. So you get this kind of coupled diffusion relaxation phenomena going on. But the Fickian assumption that bothered me the most was that there was no consideration of the interaction between the polymer and the penetrant. So the polymer and the water, which is obviously not accurate, just based on the chemistry of the polymer. So the model I developed back then, which is shown here, actually includes terms that describe and incorporate the probability per unit time that a diffusing molecule is going to become bound to a site in the polymer network, and the probability that a bound molecule will become unbound and be free to diffuse again. So I'm going all the way back to this for just a second, because this is really the genesis of the work that I'm doing now. And to sum it up, it's really the premise that water isn't just passively diffusing through a polymer, it's interacting with defects, with flaws, with inclusions, with polar sites, with other water molecules. It's a very dynamic process. This is just a brief animation. Not super important, but it shows you that, we kind of named this hindered diffusion because the effect of that interaction is that it slows diffusion. So much so that in many cases, you get this kind of pseudo equilibrium moisture content that meets the criteria for maximum saturation according to that ASTM specification. So basically the moisture content levels off at a stage where it doesn't go up by a certain amount in a certain amount of time. You say, hey, this is the maximum moisture content, and then you base all your design decisions on that. But in fact, it continues to rise for years after that. One of the papers I published shows it's 5 years of experimental data on diffusion. It's remarkable what happens after it's already met the ASTM criteria for maximum saturation. It keeps going considerably. All right, so fast forward to my first year at the University of Miami in 2012. Air Force put out an RFP related to radome performance and degradation. And given my familiarity with radome, with my background in environmental degradation, applied for that for the most part against like some of the big contractors, Boeing, Northrop, Lockheed, and some smaller ones as well. But we ended up getting that. There were 2 of them focused on 3 airframes, B-52, E-3, and B-1. The problem was that the radomes were generally structurally sound, but they were failing electrical tests. And so they'd have to scrap them, and these things were, $200,000, $300,000, $400,000 a piece. So it was a big problem. So if anybody's not familiar with radomes, their function is just to protect the radar, which you see here in this picture on the left, and protect it from weather impact, obviously improve aerodynamic performance, but still be transparent at microwave frequencies. So those are 2 contracts, 1.75 million total, 750 to me at Miami. But back to moisture absorption for just a second, relative to this. So water, unlike the typical glass epoxy composite that radomes are made out of, water is not transparent to radar, particularly not in the typical military radar bands. And so this is the operating principle of microwaves after all, right? So water is a dipolar molecule, of course, and microwaves are designed to provide this oscillating field at about 2.4 gigahertz, which is at 2.4 gigahertz because that's where you maximize the rotation of the molecule and you generate heat, right? So that's what's heating up your food in a microwave. So even a small amount of water in a radome can have a large impact on radar attenuation, baseline radar attenuation. So we expected that water content would be directly related with radar transmissivity, which we measure kind of typically as relative permittivity, at least to start. The relative permittivity of water is about 80 at these frequencies, and epoxy glass is about 3. What we didn't expect was that there'd be this kind of nonlinear relationship between water content and relative permittivity that none of the existing effective medium theories could predict. But because of my background in diffusion and water polymer interaction, it didn't take long for me to make the connection between water content and relative permittivity and the degree of water interaction with the material. So we'll talk about water type for just a second. So water was the primary culprit causing premature failure of these radomes as expected. What we didn't expect was that the threshold water content that caused radomes to fail their far field test was inconsistent. So for some it was 0.5%, for others it was 2%. So radar attenuation wasn't just a function of water content, it was a function of water content and water type. So older radomes that had been damaged in some way, for instance, by hail, would fail electrical tests, while radomes that had roughly the same amount of absorbed water would not. The hypothesis was that the bulk relative permittivity of a composite was governed by a combination of 3 things really: the base relative permittivity, the amount of water absorbed in the material, which is usually around 1 to 2% by weight, but also the distribution of water states between completely free to rotate on one end and then firmly bound on the other end, or hydrogen bound. So we still have a lot of work to do, but everything to date has shown that hypothesis to be accurate. Okay, so this is kind of getting up to where I am today. So the question became, now what? And this is kind of the genesis behind my career application. So we know a few things. One, that water molecules are always present in a composite, regardless of the operating environment. So even in hot, dry environments, deserts, you're going to get 0.5% moisture content by weight. A place like Miami, you're going to get 2 or 3% by weight. Water molecules always there. We know they interact with the polymer. That's been well established through NIR, other techniques. We know that the physical and chemical state of the material governs the degree of that interaction. And we know that that interaction influences the ability of that dipolar water molecule to rotate unimpeded with that applied electromagnetic field. And we can measure that rotational restriction using dielectric analysis at these frequencies. So then the overall question of the career award is, can we use that information to shed light on changes in the physical or chemical state of the composite at stages earlier than what we could have done before, right? Just based on, we're looking at a truly molecular phenomenon. And then what I'm talking about specifically today is, can we use that information to detect areas of damage? All right, so water as an imaging agent. So if we can determine the spatial distribution of water by type within a composite with high accuracy, and then connect that to the physical and chemical state of the material in that area, we should be able to identify locations that are different than the surrounding area, including areas of physical damage that may not be visible. That's the hypothesis. So the way we do that is through this kind of custom device we call a split post dielectric resonator. Extremely accurate way to measure relative permittivity. So you have a cavity that resonates at a very specific frequency. In this case, in the microwave range, we have resonant cavities in the lab built to resonate at 2.5, 5, and 10 gigahertz. So you insert the material under test, it causes this downward shift in the resonant frequency and the quality factor from which you can back out the relative permittivity of the portion of the material inside that aperture, inside that circular cavity, with pretty remarkable accuracy. So then you can apply that to kind of mapping, a composite. So it's constructed so that you can move a sample freely between the upper and lower resonators, which lends itself to measuring the relative permittivity at different points in a sample. So we used a combination of, some stepper motors and Arduino, MATLAB scripts to control the network analyzer that generates the signal and controls a sample location simultaneously. And so we're able to generate this two-dimensional map of dielectric properties and relative permittivity. So the overall concept is the same to what I just mentioned on the previous slide. We're just rapidly scanning the sample, but by moving the sample itself instead of the SPDR. All right, so in order to kind of explore our ability to detect isolated damage, we decided to simulate one of the more common types of composite damage that I saw when I worked at the Air Force, which is a dropped tool. Isn't dissimilar in terms of energy level from hail damage. So for this, we used the drop tower in 1001 that you see on the side here, hemispherical impactor tip. In the middle, you see some side-by-side examples of what a 4, 5, 6, 7 joule impact looks like from the front and back side on both the painted and unpainted composite. So not super visible at the lower impact levels, right? You would never guess that there was damage there just by looking at it. You couldn't detect that damage, with a tap test or anything of that nature, right? But it's still very much there. So we started by doing a single central axis scan along the full length of the sample from 0 to 60 millimeters in this case, where the impact damage is located at 30 millimeters. So on the left, you can see a scan of the undamaged sample as it gained moisture. So we're fabricating the samples, cutting them into size using a diamond saw, drying them out completely using a vacuum oven until we had a stable weight. Then we're exposing the sample to moisture immersion sometimes, high relative humidity environments, or in most cases, just a monitored lab environment, so about 25°C and 50% relative humidity. So you can see the relative permittivity start to go up consistently throughout the sample as moisture content increases from fully dry to about 0.6% moisture content by weight. On the bottom left, you get the reverse scenario, which is basically the same as the absorption case, but now we're removing water from the composite and measuring it across that central axis as we do. So on the top right, we've got a 3 joule impact damage sample. We're exposing it to moisture, and then we measured the relative permittivity along that central axis as the moisture content increased. And on the bottom right, we've done the same thing, but during desorption. So there's a few things I want to point out here that are interesting and really important. So first, notice how dramatically the relative permittivity changes at the impact site at even 0.06% moisture. That's virtually no water at all. It's actually a challenge to get such a small moisture content. To get this scan at the fully dry state, you have to keep the sample in a very nearly 0% humidity environment chamber using desiccant. And once you take it out of that environment and expose it to lab air, it's going to get to 0.06% moisture content in a matter of 5 to 10 minutes. In the undamaged areas kind of around, in that blue area, you get this consistent baseline increase in relative permittivity as moisture content increases. But in the center, it's extremely exaggerated. You get a slight depression in relative permittivity due to the damage alone right at the beginning. It's that orange line on the bottom. Probably due to just some kind of fundamental changes due to their impact. So during absorption, in the upper right, this looks incredible, right? Very sensitive to damage. But here on the bottom right is where you start to see problems. These problems weren't unexpected, but they were definitely unwelcome. But as you start to move in the other direction and you start to see moisture leaving the sample, the damaged area, which is home to far more mobile type water than any other area. And remember that mobile type water is what's actually causing all the radar attenuation. So its relative permittivity is very high. So you start to lose all that mobile type water, which means the relative permittivity drops precipitously in that specific area as soon as you start going the other way, desorbing, even though the baseline moisture content and relative permittivity remains pretty high. So it's so pronounced that by 0.3% moisture content by weight of the entire sample, you actually see a depression there where the relative permittivity in the damaged area is less than the average relative permittivity elsewhere. Because the water there is more mobile, it desorbs faster. So this is a problem. This is a big problem. But let's set that aside for a minute. We'll circle back to it and kind of talk about how we're trying to overcome that. All right. So what I'm showing here are the results when you expand to a two-dimensional grid with the scanning setup I showed previously. On the right, you have the two lowest energy impact levels and increasing moisture content from 0.05% to 0.6%. Obviously, you see a very clear indication of damage based on the relative permittivity changes. On the left, what we've done is train a machine learning model to take not relative permittivity, but just raw Q factor and resonant frequency as inputs instead of relative permittivity, and then do a simple binary classification problem where you're dividing pixels into damaged and undamaged. And I'm actually really excited about the progress we're making using machine learning to increase efficiency and lower scan time and improve accuracy. So all the results are good. All right, we can easily identify damaged areas at extremely low moisture levels, extremely low, very low levels of impact damage, levels that would be difficult to detect with any other NDE method. But here's the problem again, right? So this is the two-dimensional version of the same problem that I showed previously. So these scans are for 3 different samples, one with a 2 joule impact, one with 3, and one undamaged. So for each of those, we took a scan at 0.45% moisture during absorption. So we ended up going up to over 0.6, and then again on the way back down at 0.45% during desorption. So the 2 joule sample during desorption on the right here, by 0.45% moisture, you can see that the relative permittivity of the damaged area is less than the surrounding area, which is what we saw on the central axis scans as well. So, but the 2 joule sample, you see no damage at all, right? So it's completely, there's obvious that there's blind spots at certain moisture contents and damage levels and absorption, desorption history that are going to be problematic if you want to use this as an NDE technique. All right. Oh, sorry, Chris. All right. So, but this is a great segue into some of the challenges and limitations, right? So first, using the dielectric technique, and this is the one people usually identify first, but using this dielectric technique, you're limited to non-conductive materials, right? So carbon fiber becomes a problem. But the innovation really is using water as an imaging agent, right? So any technique that you can use to identify the water states has potential for this. And NIR, it turns out, may actually be a better way to exploit water state for damage detection. I'll show some early results on that. Secondly, the SPDR, the resonator, is impractical outside of a lab, largely because it requires both sides. It may have great potential for something like an assembly line application, but you're not going to be able to use it in the field, at least for most applications. If you want to inspect an aircraft structure, marine structure, oil and gas pipeline, which you think might do really well for that, you have to have one-sided access. So we're looking at using spot focusing horn antennas for that. Talk about that super briefly. And lastly, as we just saw, the method is susceptible to environmental history. So I'll spend a minute talking about how we're using damage-dependent hysteresis to overcome that challenge and get rid of the need for baseline subtraction as well. But first, this conductive material problem, just really briefly, early results using NIR. NIR is a great way to separate free and bound water. So you have distinct peaks here on the left for free water. And on the right, you see the ratio between the concentration of free and bound water changes according to moisture content. You get this kind of slow decrease. And to damage, though, you see that 5 and 3 joule damage sample showing a much higher ratio of free to bound water as expected, but NIR is picking it up really accurately. So seeing some really promising early results with NIR that may allow us to overcome that non-conductive material limitation while still leveraging water states to detect damage. The big question, this is still a big question mark, are free space techniques going to be accurate enough? And the answer is, I don't know. I think it's 50-50, but this is one of the things we'll be exploring very soon. We've got our spot focusing horn antennas in the lab, got them hooked up. It's just, a question, are we going to be able to generate enough accuracy for it to detect damage and at what levels and things like that. But it should allow, if you use it in this kind of reflectance mode, it should allow one-sided access. So we'll see. But But the big thing that we've spent a lot of time on lately and that I'm excited about is this kind of damage dependent hysteresis. So we've shown that using this method overall, you can really accurately identify areas of damage, even at moisture contents that are, less than 0.1%. But it requires a few things. The first is establishing a dry baseline so you can distinguish areas that have a higher relative permittivity due to the presence of water. And it requires that you take measurements during the absorption phase only. With respect to getting a dry baseline, the method is so sensitive that even a slight variation in the thickness of the sample, for example, can show a dramatic difference in relative permittivity when you map it. And without subtracting the dry map, you might classify an area that's slightly thicker as being damaged when in fact it's not. So to get around this, we're trying to leverage the fact that damaged areas have a higher concentration of free mobile water, which is why the relative permittivity is higher. But this also means that because mobile water is more mobile, it's moving in and out of the material more easily in this damaged area. So what you get is a steady kind of slow increase or decrease as relative humidity goes up and down in most areas of the material. But in damaged areas, these changes are much faster and it's much more responsive to the atmospheric conditions. So to put it another way, what you're really looking for is not necessarily changes in the spatial distribution of dielectric properties. What you're looking for is like a temporal change in that spatial map. So more specifically, areas that change rapidly in response to a slightly changed environmental condition, as opposed to areas that lag behind and change more slowly. So areas of rapid change in dielectric properties have a higher concentration of mobile water, which is associated with damage. So, you might, imagine in terms of application, imagine like a test rig at a depot maintenance shop where you can scan a composite structure, get a relative permittivity map, and then expose it to high humidity or low humidity for that matter, or even spray it with water, right? And then you scan it again. And when you subtract those two scans, you're going to see hot spots. So areas where the scans differ significantly. And those areas are likely the ones where you've seen a tool drop or other type of impact, and you've got, even if it's just a temporary, higher concentration of mobile water in those areas. Anyway, the hysteresis loops, back to this for a second. So if you plot these during absorption and desorption, the size of the hysteresis loop is directly correlated to the extent of damage, far more accurately than just the change in relative permittivity. And this also means you don't have to use that baseline subtraction. So on the top, you see x-axis is change in relative permittivity, but on the bottom, it's absolute relative permittivity. Now, obviously, you need multiple measurements at different points of time, but at least you don't have to know the exact baseline relative permittivity of the sample in this method. You can take a scan at any time. The other thing that this method does that's really interesting, at least at this stage, is that it increases our sensitivity. So instead of using the change in relative permittivity to classify, a pixel into damaged and undamaged, we're using the residual sum of squares from the hysteresis loop, compared to that line of best fit, and using that method, which is basically just an area, it just gives us a sense of the area of the loop. And using that, the ratio of a damaged to an undamaged area is in the hundreds, like you see in the middle left here, as opposed to like less than 3 if you're just using relative permittivity. So there's a potential there to make the method far more sensitive. It's a little more cumbersome in terms of scanning, but it could be far more sensitive that way. In terms of progress, next steps for this project specifically, we've published 4 papers so far, 1 in review, several others in prep. So that's been in soft matter, polymer composites, composite structures, composites B, computational material science, I think is one of them, all pretty high impact journals. The reception of the work's been very good. We filed 2 invention disclosures for that method, and we're actively kind of seeking businesses to partner with for further development and licensing. There's several active sub-projects, including that free space method, using the technique for in-situ measurements during fatigue. We've had a lot of success using MD simulations as well. In terms of next steps, we decided to kind of split this damage detection part off from the career award and pursue it independently, which is going to let us focus more on the fundamental science and mechanics insights that this method kind of enables. And so we'll try to partner with a small business for the applied part of damage detection and leverage my experience with the STTR, SPIR mechanisms to get some funding that way, which I think is our best bet for something of such an applied nature. We're also actively trying to kind of outline and really get a good sense of scan resolution and detection limits. One of my PhD students, Katie, actually just presented this at a conference last week, and I'll talk about that really briefly in just a second. This is one of the more exciting things that's coming up, is this in-situ damage progression during fatigue. So the SPDR is set up so that a sample can actually pass through the resonant cavity and then be gripped on either side in our fatigue machine. And then you can monitor the dielectric response in real time as we cycle it. It's very preliminary, but we're seeing some interesting results that I'm really excited to dive into. So on the right here, on the left, you can kind of see how the sample passes through the SPDR and is gripped on either side. But on the right, you see two composite samples, one with about a 0.5% moisture content to start and the other one dry. And then over time, as damage accumulates, you see this steady rise in relative permittivity in the moisture contaminated sample and not in the dry sample. The sinusoidal thing there you see, by the way, is just an artifact having to do with the timing of the fatigue cycling compared to the timing of the dielectric snapshot. So you get this kind of sinusoidal thing. But the overall trend shows an increase in relative permittivity, which may mean that we're seeing absorbed moisture move gradually from the bound to the free state over time due to accumulating damage, which is kind of the hypothesis, but still too early to say that with much confidence. But I'm hopeful that this method allows us to observe and track fatigue damage starting at a much earlier stage than any other method, and to do so non-destructively, right? So you can track it through the entire cycle. But we'll see. That I'm really excited about where we could go with that. And like I said, Katie just presented some of this work. I won't spend a lot of time on it. She presented it actually last week. But she's exploring kind of, how do we optimize scanning time and effort. And the results, so far have been great. And it showed that even at low resolution, taking a snapshot every 5 by 5 millimeters and very low moisture content on the order of 0.05, you can identify the damage boundary around an impact area with really high accuracy. Okay, I think we're doing okay on time. I'll still have time to talk about a few other things, but kind of a summary of this damage detection sub-project. The first thing is that the primary value may be, as we always anticipated, in a lab setting, to kind of shed light on the damage initiation and growth, kind of fundamental science, fundamental mechanics. But I do feel like there's a high potential for the use of the method as a new NDE technique in certain applications. It's highly sensitive to damage, it's fast, it's simple, it's low cost. It certainly has challenges and limitations that we have to overcome. The conductive material one is a big one. Expanding it to free space techniques so you can apply it in the field. Multiple moisture states at various times are really required to get that, so you're not dealing with the desorption problem. And we need to get scan speed and resolution and accuracy really dialed in before we'll know if it's going to be a competitive technology. But I do have high hopes for it, and I think at the very least we'll get some funding to continue exploring it on its own. Okay, so because I have some time left as expected here, I wanted to touch briefly on some other projects, starting with this one, right? So the work I've done with NIH. So it's been funded through the R41 through 44 mechanisms, which are phase 1 and phase 2 SPIR and STTRs. And for those of you who aren't familiar with those mechanisms, in terms of review and funding decisions, they function exactly like the more well-known R01 or any other mechanism at NIH. So a common misconception is that you submit a proposal to your industry partner, which is not true, right? You submit the proposal directly to the NIH. It goes to a panel of experts, primarily people in academia. It's discussed or not and scored or not. And based on that score, it goes to council and it's either funded or rejected. So it's the same process as any other NIH funding. Funding rates, though, for this mechanism are slightly higher than they would be for an R01. So for R41, it's about 10 to 15% of proposals are funded, depending on the institute, which is, anybody who's submitted an R01, sometimes, you're talking about 5-6% funding, 7%. So it's about double that. It's more in line with NSF success rates. Phase 1 is 1 year, maximum 225, although I actually think that went up to 250,000 for feasibility proof of concept for 1 year. I think it went up this year. You have to partner with industry because the funds are strictly federal flow through from a small business to the university. However, with an STTR, which if anybody does this, I would encourage you to do an STTR, which means there's only one PI for the full grant, and that person has to be at the university. So if you look at the notice of award here on the bottom, like and how it's set up, it shows me as a principal investigator. It even has our address there, right? So it gives you a little more control to the university through this mechanism. The downside, of course, is that even though the PI at the university is in control, you're limited to about 60% of the total funds because the small business has to take 40%. So it's about 125,000 for the year for you at the university. And this is the one that was focused on that pressure sensing film that I actually designed while at Miami, combining that with some machine learning techniques. But I'll talk more about that in just a second. The other one, so the R42 and 44 mechanisms are phase 2. So this is after proving technical feasibility, and these are larger $1.7 million grants over 2 years. So there's quite a bit of money involved, subject to the same stipulations regarding distribution of funds. For these, it's a 12-page research strategy and a 12-page commercialization plan. But keep in mind that the review panel are almost wholly academics or former academics. So in my experience, 90% of the score actually comes from the research side, not the commercialization plan, which is maybe not how it should be, but that's how it is. This one is a combination of systems engineering. It's very machine learning focused. I wrote this proposal in January, got a notice of intent this spring, and it was awarded in August with a September 1 start date. Unfortunately, the college is dragging their feet a little bit, so we haven't really been able to get started on the university side. But that should happen pretty quick. Quick word of caution, I guess, for people trying to pursue these mechanisms. This is an SBIR, right? So the PI is at the company, which is not ideal. So I would encourage you to do STTR. And there's certainly benefits to working with a small business and working with other investigators from other departments. This particular one, Dr. Mayorga and Julie Ivy in ISC are on it, Min Shi in computer science, Ann McLaughlin in human factors. My mistake on this one is that, I wrote 90% of this grant, maybe more, but I only get about 10% of the credit because I'm only getting about 10% of the budget, which is pretty painful. So I guess the lesson here is, don't put more effort into the grant writing than you'll receive in total funding, which is something I probably should have known. But the silver lining is that, now I know what it takes to get a really incredible score on a phase 2 proposal, and I know I can do it. So in January, I'll submit a phase 2 proposal for the phase 1 work that just ended, that I'll talk about right after this, with myself as a single PI, and with about $1 million, about 60% of the 1.7 coming to NC State. The last thing, and so I'm really excited about that. And I think there are a lot of reasons that I think we have a really good chance of getting that phase 2. Not only the success of the phase 1, and we've proven technical feasibility, but some of the things that are happening congressionally and with the Center for Medicaid and Medicaid Services and HHS, I think we got a good chance. But I wanted to bring up these mechanisms because I think they're incredibly underutilized. And to me, this is the perfect mechanism for engineering. It's a combination of basic and applied science, which is what we do. And so I'd encourage everybody to explore those if they can. The other benefit is that it's an easy way to get your foot in the door with industry partners. If you can identify a small business, which is less than 500 people, so it's not even that small, somebody that works in a similar space to you, almost all of them are going to be interested in this kind of funding. That local polymer film company I worked with during COVID, Polyzen, they actually gave me $25,000 just to explore opportunities to write an STTR with them, which I expect to do early next year. So they gave me kind of an initial award just to look at pursuing an STTR. And I'm happy to, either after this or at any time answer any questions about those mechanisms, which I think should be obvious. I'm a big fan. All right, so this phase 1 STTR that just ended in August, it involves a pressure sensing composite film. So this kind of still falls within my general theme of like environmental response of composites. In this case, the electrical response of the film changes when you're interacting with it from a tactile perspective, right? When you're applying pressure. So this was an architecture I developed when I was at Miami. We were using it to monitor proptosis around the eye, swelling around the eye and nexa during prone surgeries to prevent post-operative vision loss. But we've applied that here as well. And there's an integrated accelerometer. So you get the data from the film, the accelerometer, they're transmitted via Bluetooth. So the premise, companies like Facebook, right? They monitor what you're doing on your phone and they send you targeted ads based on that data. Very effective. And what we're trying to do here is really the same concept. We're collecting data about how people are interacting or not interacting with their medication. This medication helps them keep their vision, and using that to design interventions at exactly the right time for the right person. So it's kind of a better application of that kind of concept. Glaucoma is a massive problem on a global scale. It's actually the leading cause of blindness in the world. And at the root of it is this high intraocular pressure, which causes damage to something called the lamina cribrosa, which is where the optic nerve inserts into the globe. And that material is actually a composite, collagen fibers. And it's reacting to an environment, high pressure, and various other things that are causing it to degrade, which leads to glaucoma. And Dr. Kuznetsov and I have actually published some papers and received some funding for studying the biomechanics of the lamina and its response to that pressure gradient. Anyway, intraocular pressure, it can be well controlled with daily drops, but fewer than 10% of people actually do those because they hurt, they're hard to remember, they actually make your eyes feel dry and gritty. Whereas having high pressure doesn't hurt. You don't know what's happening, the damage is still accumulating though. So adherence is a major problem. But with this, the bottle label becomes a smart sensor, lets us know exactly how you're interacting with the bottle. We can see, when you try to take a drop, when you take the cap off and you put the cap back on, when you miss with a drop, how often you get too many drops out, how much medication you have left, when you're carrying it around, when you're tossing it around. All that information gets fed back to a system which automatically recommends certain interventions based on that data. And I actually am really excited. We got about 20 minutes before this seminar, we got from the company that's manufacturing the chip. I don't know if you guys will be able to see that, but it actually just came in the mail, the prototype. So I'm pretty excited to get those on a bottle and see how they perform. Very difficult to get, as you know, because of the chip shortage. Anyway, so I think I have a few minutes. I'll talk about COVID stuff. I know we don't hear enough about COVID in our daily lives, right? So I'm sure everybody will enjoy this. So I want to talk about it for a few reasons. The first is that this was easily the most difficult and most challenging thing I've ever done in my entire life by far. Mentally, physically exhausting to a degree I've never really experienced before. I was spending 80 hours a week on COVID stuff for months. Obviously physically exhausting, but the mental and emotional toll was pretty high as well. It was pretty high stakes, high pressure at the time. There was a lot of fear, as I'm sure everybody remembers. We didn't know what was going on. So we were, fortunately I was able to manage a team of 12 to 15 people, mostly grad students, managing $1 million in funds that came in, within a few months, managing all the legal implications and things like that, working with the legal office at NC State. And by April, I was also managing, getting dozens of pretty desperate pleas for help daily. everything from parents wanting something to protect their immunocompromised child to large hospital system looking for tens of thousands of something. My wife was only doing emergency surgeries at the time, so she was home a lot, and she actually had to manage my email inbox for me and respond to these people because I felt they deserved responses, because the fear was, very real at that time, but I just couldn't keep up. So she was managing my inbox. Second reason I want to talk about it, and Srinath, thanks for mentioning this at the beginning, because I've never done anything as rewarding as this. And of all my accomplishments in my career, this is actually the one that I'm most proud of. But there's not really a good spot for it to show up in my dossier, right? So it's not really highlighted. So I appreciate the opportunity to talk about it a little here. Also really proud of the department and the college and how they responded and supported me throughout, and the grad students. And most of all, the students who worked alongside me every minute of every day were incredible. But so what we ended up doing, we designed a product and a process, for building these disposable lens cuff combinations for powered air purifying respirators. And we went from a prototype to a final product in about 2 weeks, including passing all of the tests with the, what do they call it, infectious disease department at UNC. So it was a really, really rapid. We ultimately delivered about 150,000 of these nationwide, all of which we either fabricated in EB3 or used the tooling that we designed and built in EB3. And then we designed several other products from scratch for use in ICUs and emergency departments, reverse engineered dozens of other medical devices and items. I honestly lost track. I'll show some pictures of some things. It ended up being over $1 million in funds. It came in from WakeMed, UNC, Cone Health, hospitals in California, New York, Chicago, over 3 or 4 months starting in March 2020. So it was a lot. It was a lot to handle. Unfortunately, only 64K of that showed up as research, right? So it doesn't really reflect the effort, when you look at my dossier. But there was that subsequent 25K grant from Polyzen, just based on the relationship that we built through COVID, and hopefully that will continue. On the bottom right is my dining room table in March of 2020, much to my wife's dismay. But that's kind of how my house looked for many months there. Here's just some pictures, some of the things we designed and manufactured. In the upper left, you see one of those capper lenses. It's powered air purifying respirator. I don't know what the C stands for. I think it's contained or something like that. But these are disposable. They go through a lot of them. You can see on this picture just next to it how they function. So they attach it to a helmet with a fan built into it, which creates this positive pressure environment around the person's face. So it has to have a clear lens, but also this attached polymer film that comes down under the chin to create a seal. And we had all kinds of problems sourcing materials for these things. I spent a lot of time on the phone with various plastic suppliers, trying to get what we needed, and we often couldn't get what we needed, right? So we had to adapt our processes and our designs to the supplies that were available. One of the things I'm most proud of is the welding process we developed for attaching this flexible film to the PETG. So you can see it here kind of on around this curved section. All we could find at the time were these electric griddles from Target. So I went to Target, picked up 3 of these $25 electric griddles, and we took them apart and developed a welding fixture using those, and it worked incredibly well and still works incredibly well. In the middle here is a picture, Srinath alluded to, we got some good feedback to the department. This was, I think, posted on Facebook, but we made sure we sent all of these out the door with a sticker right on the middle and the front that had the MAE logo on it. So we got a lot of really positive feedback from the healthcare community for that. And at that time, like I said, so much fear and uncertainty that around the virus that people were terrified and super thankful to have this kind of protection. One of the other things we designed and built was this innovation shield you see on the right. So the biggest risk to people in the ICU was during intubation. And so they needed good visibility, space to work. So they called me. I spent a lot of time in the ICUs kind of observing, and then we designed and built about 80 of these shields that are still deployed in ICUs and emergency rooms around the department. I actually just saw one at Rex, in the Rex ER when I was unfortunately there. On the bottom left is another thing. This is called a PEEP valve, which is used for ventilators. last summer, these just couldn't be found. So we designed and built these using a combination of 3D printed parts, off-the-shelf PVC from Lowe's. We built an emergency ventilator as well, which fortunately was never used. It used a windshield wiper motor as a driving mechanism. The governor's office actually coordinated that. So it was me, several people from UNC, and some local industry. And in the bottom of the middle, just a few of the dozens of little parts that we reverse engineered and fabricated, just little things that no one thought much about until they couldn't get them. And then everyone panicked and they came to us and they'd bring us one of them, we'd reverse engineer it and 3D print it in most cases. And I have to mention the student volunteers because they can't really stress enough how incredible they were. So I had to put them up here. Hopefully I've gotten everybody up here, but leading this group was an incredible honor. They all really rose to the challenge. Not only were they working hard and putting in a lot of hours, they were innovating. One of the things that I pushed really hard from the beginning was that, I was determined that we weren't going to become an assembly line. Our role was to innovate, to solve problems, develop new products, processes, improve them. And they all really took that to heart, and they never settled for a process just because it worked well enough. They were always improving. So once we had something down, we looked for local partners to take on the fabrication and shift that assembly line work elsewhere. So Polyzen, SAS, actually the software company, did a lot for us. They had a machine shop that was sitting idle. And so we shifted a bunch of stuff over to them, and they were thankful to have something to do. But I had to put these students' names up there because they were incredible. And I can't leave out Srinath, who was often right there alongside us, making sure we had everything we needed, providing lunch every day when the hospitals didn't, and reminding us to wear our masks just about every day. And of course, Paula and Tony, I couldn't have, managing that $1 million that came in so quickly would have been impossible without them. And a lot of other people as well. Tim Horn had, I haven't even touched on what he had going on, which was kept him super busy too. And then kind of in concluding, I have to acknowledge my PhD students who contributed to at least some of the work that I showed here. As everybody knows, and I've learned over the last 9 years that there's nothing more important than having high quality PhD students, especially as you work toward tenure. At Miami, I graduated 3 students that all contributed in some way to the work I mentioned today. Luis is at NASA Glenn now. Mauro in the middle took a gamble and joined a biomaterial startup that had, I think, 14 employees at the time, but now has hundreds. His salary's about triple mine, which is painful, but I'm proud of him and happy for him. Bridget actually works in management at Carnival Cruise Lines, of all things. Graduated from MIT, NSF graduate research fellow, great student, but decided to go into management. I'm sure she'll do well. And then at NC State, Idolor graduated earlier this year, and most of the work related to damage detection I presented today was his. Incredibly talented, incredibly hardworking student. He's in Atlanta working for Exponent now. Omkar is defending next month and has a job lined up as a research associate with Virginia Tech starting in January. Rishab's graduating in 2022. I'd be surprised if he doesn't end up in a tenure track position in a few years at a top tier school. He's very bright. Anybody who's had him in class knows how bright he is. And then Katie, my newest student, she'll graduate in 2023 probably. She's a former REU student from UMBC that we tried to recruit and did so successfully. And so she's been around the lab for a while now, is a huge contributor. And then just kind of acknowledging the funding agencies that contributed to the work I mentioned, starting all the way back at Miami. And with that, thanks for bearing with me. I know I went through a lot of stuff there at the end. Got through a lot of material, but happy to answer any questions anyone has. And for those of you who are watching this on the recording, which I hope is a lot, feel free to send me questions via email.
In the interest of time, Landon, we are not going to take questions because
no questions. Okay.
People have.
We do have a hard stop. Sorry.
Hard stop, and also that people can email you questions.
Yeah, happy to answer questions.
This is more out of for your information from your own words, what your research has been the last 5 years here and how you have developed your program and what your contributions are. I think you made that very clear, and And I just want to tell you, as one of the reasons we were successful in the PPE is that the students followed the rules with the masks, and we didn't have a single outbreak in over 4 months of work.
Yeah.
And
Yeah.
that has been pointed out to me every time I meet with John Gilligan or
Yeah.
Nathan Wook. They always point out how good we were with maintaining the rules. And I think it goes to the credit of you and the students for maintaining a clean and safe environment while doing all that stuff. So
they were incredible. I'm still impressed.
of course, I had to tell people to put the masks on, but
Yeah, of course. Yeah.
that was my job. But I mean, I did contribute in a different way. But I just want to thank you for that and appreciate it. And everybody, please send your emails directly to Landon. He can answer questions, or you can meet him at coffee on the corner here, and then talk about it. But in the interest of time, I'm going to put a hard stop on this, and thank you again.
All right. Thank you. Thanks, everybody.